Welcome to the Environmental Design Digital Media Center's 3D printer certification video. In this video, you'll learn everything you need to know to get a successful 3D print from one of the Lulzbot TAS 6 or Lulzbot Mini 2 3D printers available at ENVD. Before watching this video, I recommend spending some time getting familiar with a 3D modeling program like Rhino so that you can understand the basics of 3D modeling. However, it would be a good idea to watch this video before you start modeling the specific item that you intend to 3D print, so that you understand the printer's specialties and limitations and can incorporate that knowledge into your design process. After this video is finished, you'll be asked to take a quiz to ensure that you've understood the material. Then, you'll be certified to operate the printers here in the DMC. All the 3D printing in the DMC is run by you, and we do not offer a drop-off 3D print service. You'll come in, check in with the lab supervisor or a student worker, and they'll get you equipped with the supplies you'll need. Typically, the printers in the DMC are used on a first-come, first-served basis. This is because it's kind of tough to predict just how long you'll need the printer for until you come in and start printing. You're expected to configure and start your print, monitor it throughout, stop and restart it if it messes up, and collect your print when it's finished. You don't have to stay in the room the entire time. We'll have a label for you to mark the printer as occupied so that you can leave a print running on it. However, if your print is malfunctioning and you're not around to fix it, we're going to stop the print without restarting it. So if you're 3D printing, it's a good idea to check in often and block off some time for you to work on that project. If you intend for a print to run overnight, you must start that print no later than 1 hour before we close. When printers run unsupervised, there's a big risk that a failed print will end up harming the machine, so we need to be able to see how a print is doing before we decide to let it run overnight. Now, if you want to set up and preview your print before you come in, you can do it by downloading a program called Cura for Lulzbot and setting it up per the instructions that follow later in this video. This is not mandatory, however, as we have a PC with Cura here for you to use as well. So those are the rules you need to know. Let's get started by learning a little bit about the basics of 3D printing. The term 3D printing refers to a growing spectrum of technologies that take advantage of a technique called additive manufacturing in order to create a three-dimensional object from a digital design file layer by layer. Additive, in this case, differentiates 3D printing from subtractive manufacturing methods like CNC routing and laser cutting, as well as production line injection molding. While 3D printing certainly does not make these other technologies obsolete, the ability to easily create certain types of shapes that other methods can't produce using design software now commonly available to the average consumer makes 3D printing an exciting fabrication and prototyping tool, and we're only beginning to scratch the surface of what 3D printing is capable of. The methods used to 3D print an object vary greatly, with some technologies offering greater levels of detail, a wider variety of materials, faster and more detailed prints, or even multiple colors and finishing styles. There are printers that use selective laser sintering technology to fuse fine powders together into a shape, leaving behind the unfused powder to fill the negative space. When it's done, the excess powder can be recycled into the next print. Other printers take advantage of a photochemical reaction that occurs when a laser is shined at a pool of resin. The resin hardens and attaches to the platform that rises up from the surface of the pool as subsequent layers continue to be generated. The most commonly available 3D printing technology is called fused deposition modeling. If you've seen or used a 3D printer before, this is probably the kind you've encountered. The plastic comes loaded onto spools which mount to the side of the printer and get routed through a print head called an extruder. Like a hot glue gun on a computer-guided track, an FDM printer relies on a hot nozzle to extrude strands of molten plastic onto a plate. Using belts and motors, the extruder and plate are moved along the X and Y axes, drawing a horizontal pattern to express a single slice of the modeled object, beginning from the bottom up. The plastic adheres to the plate, cools, and hardens. Then the extruder moves upwards slightly on the Z-axis and starts the process all over again, continuing to stack more and more layers to create the object one slice at a time. It all sounds very slick and impressive, but there are a lot of unexpected downsides to FDM 3D printing that you don't always hear about in the typical 3D printing sales pitch. It's important to be aware of these limitations before you get too far in your design. For starters, the quality of the printed object isn't always great. FDM printing leaves a rough, layered surface that isn't always attractive, and sanding it down to a smooth exterior can be more challenging than you think. Thin parts can be very fragile, more fragile than if the same component were to be made via injection molding, because a 3D printed object contains natural break points due to its layered construction. Print quality and success rate can also tank if the plastic spools are too old or have been exposed to too much atmospheric moisture. We try to avoid keeping any one spool laying around for more than 6 months, which is why our selection of colors isn't as wide as we'd wish. Keep this in mind if you're planning to spend a bunch of money on spools of your own, and make sure to keep them sealed and store them in a dry place. 3D printing is also slow. To print an object the size of a grape, for example, takes about 40 minutes. Something the size of a lime, an hour and a half. A peach, 3 hours and 20 minutes. And an orange, 8 hours and 45 minutes. See, printing time scales exponentially. In other words, if an object took 2 hours to print, and you double its size, it will almost certainly take much longer than 4 hours to print at its new size. So even with a big 11-inch wide plate like on the TAS 6s, it's important to consider that just because an object can technically fit in the printer, that doesn't mean that it's remotely practical to print. At the very least, not all at once. You may have to chop your object up into different components and assemble the final product afterwards, but this isn't always a perfect process either. On a 3D printer, tolerances can be very inconsistent and subject to external factors like air moisture, age, and quality of the material, and sometimes just plain bad luck. So there's no guarantee that your pieces will all fit back together perfectly. There is an entire taxonomy to the variety of errors that can occur during a 3D print, and trust me, if you're going to be doing a lot of printing, knowing this stuff in advance can save you a lot of headache. On paper, 3D printing is supposed to be pretty easy. If it all worked as advertised, this video would take 5 minutes, and all you'd have to know is how to put a file on an SD card, pop the card into the printer, load the plastic in, and press play, and that's it. Because once a 3D printer starts, you don't touch it, you just watch. You make sure that the print looks okay at the start, then you check in on it every once in a while. All the real work and skill that there is to 3D printing is in knowing what could go wrong, what to avoid, and how to design around the 3D printer's restrictions. But every single print comes with the possibility of failure, and a failed print is almost impossible to fix halfway through. A good print starts with a clean printer, which means a nozzle that doesn't have a bunch of gunk on it, and a plate that's free of dust and other debris. To understand why, you need to know about adhesion. That is, the question of whether the plastic manages to successfully stick to the plate at the beginning of the print and all the way throughout. Because if your print detaches from the plate, there's no way to just reposition it and resume. You have to start all over. Also, once a print starts sliding around the plate and getting dragged around by the nozzle, it can cause a giant mess. If plastic gunk gets too close to the nozzle, it can damage the printer and leave it out of commission until we get a new part in. Now you can usually tell if your print adhered correctly by watching how the first layer prints. But why is adhesion even a concern? Well, remember that every 3D print starts with the nozzle trying to squish down a layer of plastic onto a glass printing bed. In order to get good adhesion, your nozzle needs to be at a very specific distance from the plate, so that when the plastic gets extruded, there's just enough room for it all to come out, but just enough pressure to squish and cook it onto the plate. It's not enough for the plastic to land on the plate. That squish is important. If the extruder is set too low, the metal nozzle may fly too close to the plate, blocking its flow, and preventing plastic from flowing out at the appropriate rate. Like putting your thumb on the end of the garden hose, plastic will come out too thin, it won't form a complete base, and it may also start getting backed up further up the mechanism. On the other hand, if your nozzle is set too high, then the plastic begins to cool and curl before getting squished. When it's just right, the first layer will print like a smooth, flat ribbon. So you're probably thinking, if all this trouble comes from the nozzle being at the wrong height, how do I get my printer's nozzle to the right height? The answer is a bit silly actually, because you can't control this directly. The printer's Z calibration routine, which happens at the beginning of every print, takes care of finding the right height for us, and the way it does it is by poking the nozzle against one of these metal discs, which act as sensors. When the two metal parts make contact, they complete a circuit that tells the 3D printer, hey, I found the height of the plate. The problem is that if there's a bunch of residual plastic gunk on the end of the nozzle, that connection won't be made immediately, and so the machine will get an inaccurate reading of the printing height. And that's why it's important to keep this nozzle clean. More on how later. All of this effort at making sure we get good adhesion helps us avoid warping. Now, warping isn't only a symptom of bad adhesion, but it definitely worsens it. Still, warping is just a force that you'll probably have to deal with in some manner or other when 3D printing. Warping is what happens when the printed plastic begins to cool. As the material cools, all the plastic molecules get just a little closer together. This creates tension throughout the model that can impact the print at any point, not just the beginning. So sure, the first layer can tell you a lot about how the print will likely go, but even when all things look good, warping can still hit at any time. Warping tension is strongest at the corners of the print, and that's why objects usually curl at the corners. They'll peel off the plate entirely or experience separation between the layers. Warping can cause the print to fail, and there's little you can do to fix it. You can try to push the curled corners back down, but they're not going to stick. By the time you notice it, it's already too late to reverse it because the plastic has cooled and hardened into that shape. The only thing you can do to fight warping is to prevent it, and you can prevent it by designing intelligently. In this case, it's all about the footprint of the object. For example, if I wanted to print a rectangular rod that is 8 inches long but only 1 inch wide, it would actually be more likely to succeed if I printed it standing up vertically than if I laid it horizontal, because as a vertical pole, it would represent a smaller footprint on the printer bed. The more surface area of the plate is covered by a continuous mass of plastic, the stronger the cumulative shrinking force acting on those corners will be, and the greater the likelihood of total failure. This is why simply asking, how big is the bed, isn't really the best way to think about a 3D printer's potential. Your printer bed could be a mile long, and your objects would still start warping after about 6 inches. So you might think that the way to get around the warping issue is to break up your object into a bunch of smaller parts instead of one big mass. Or maybe you have a different reason for wanting to print multiple objects at the same time. That's not a bad idea, but it comes with some downsides. Because if 10 separate objects are printing on a single plate, each one will get the benefit of a small footprint, but if even one of them screws up, you have to start over with the whole plate. See, a 3D printer has no real sensors that tell it how well it's doing at 3D printing. It can't respond to that stimuli. It can't react to external changes or accidents. Once the plastic is out, it's out, no matter whether it landed well or it didn't. And the printer moves on, assuming it's doing the right thing. And if it doesn't lay down the plastic correctly on one object, those errors will start rippling out to everything else that's printing at the same time. Plastic that was supposed to land on one piece now starts landing on other pieces and globbing everything up. To sum it up then, the absolute safest way to ensure that your print completes is to print objects with small footprints when possible and print them one at a time so that you can bank your successes and troubleshoot the problematic objects individually rather than letting them ruin your other prints. None of these are hard and fast rules though, because there are times when you have to balance these factors against other concerns. Oh yeah, there's more. You also have to think about support material. 3D printed objects are only built upwards, meaning that every time material is deposited, it has to land on something. For any given layer, the plastic that gets printed must come to rest on the cooled hard plastic printed during the previous layer. If it does not, it'll just drip down and flop to the base plate. So what happens if you print something with an overhang? Well, if the slope of the overhang is less than about 45 degrees, it may not matter. But as you get closer to 45 and beyond, the odds that you'll need support material increases. Support material is this fragile, spongy scaffolding pattern that the printer deposits as the object is built, in anticipation of the parts that are going to be printed on top of it. It prints it in thinner strands than the actual body of the print, so it has less strength and stability than your object. This is because it is intended to be easy to break away from your final product. You can usually do it with your hands, but sometimes it can print really densely if you have a lot to support, and when that happens, it may need to be removed with a sharp and delicate tool. Support material helps you print shapes that would otherwise be unprintable, but it comes with its own drawbacks. For starters, the layers directly adjacent to the support material may come out in lower quality, feeling rougher and chunkier. You might also not be able to remove the support material from a fragile print without breaking it. Support material has a harder time sticking to the plate on the first layer. So if your print depends on a lot of support material, you may want to consider printing with a raft. And if you're expecting to print something very tall with an overhang at the top, the scaffolding might collapse before you get there. The good news is that you don't need to design support material yourself. Just design the object you want printed, and the software that sends the job to the 3D printer will figure out where to insert support. This also gives you the freedom to rotate the object and test out different orientations, since the same object might require different amounts of support material depending on whether it's right side up or upside down. Generally, you want to look for the largest totally flat surface on your model and put that directly on the bottom so that the flat surface is your first layer. Think about a simple dinner table, for example. At its normal orientation, the flat tabletop on top of the four legs practically requires a whole brick of support material to print correctly. Flipped upside down, however, the print would require 0 supports. When you are modeling your design, ask yourself, have I actually created a flat surface that this can print from, or is this giant blob going to require supports no matter which angle I rotate it to? The takeaway from all of these discussions about adhesion, warping, and support material is that if you plan to 3D print, you should always design with the limitations of the printer in mind. If you get too crazy designing intricate objects without paying attention to the decisions that might complicate the actual fabrication process, you might find yourself panicking and crossing your fingers as you attempt print after print, trying to get it just right before a big deadline. You can imagine that there will be situations where reducing warping, reducing support material, and reducing the total print time for multiple objects all conflict, and you'll have to make choices about what to prioritize. There is no single best answer. Now, sometimes the best answer is to ask yourself, does this really need to be 3D printed at all? Is this something that I could make by hand faster and more accurately? Is this something that could be laser cut or CNC'd instead? So you've decided you're going to 3D print and you need a file to feed the machine. Well, let's review the files that are involved in getting to that process. First, you've got the project file. This is the file you'd create in SketchUp or Rhino, the 3DM, for example, that contains the model with all of your edits, annotations, layers, hidden objects, etc. This file won't do you any good in terms of 3D printing, but you should of course keep it backed up so that you can export it into STLs just in case. An STL file is created when you export objects from your project file into a small and easy to exchange format. Think of an STL file as the JPEG of 3D printing. You'll lose the ability to edit its components directly, like you were able to do with your project file, but it'll be much simpler to share and smaller in size. This is the file that you want to bring to the lab so that you can slice it into G-code. How do you make G-code? Well, for that you need something called a slicer. A slicer is a software application that analyzes an STL file, divides it into layers, and figures out all the moves the 3D printer has to do to create each layer. The slicer then packages all of those instructions into G-code. G-code is a text file that contains the complete set of instructions for the printer. Like a list of points on a connect the dots image, G-code contains all the little coordinates that the nozzle has to hit, how fast to travel between them. It also declares when the printer should heat up and cool down, where to put support material, whether to print a raft or not, etc. If you're printing multiple copies of a single STL at one time, or if you'll have more than one STL on a print job, that's also going to be expressed in the G-code. STL files are universal, but each G-code file is unique depending on the model and size of the printer, the specific nozzle it's using, and the level of detail versus speed that you selected in the settings panel. But before we get that far, there's actually something else you have to worry about. When you're creating a 3D model whose only purpose is to look pretty in a still image, you can get away with a lot more errors than if you're 3D printing. For a 3D print, you have to design with a bit more care and planning. You have to ask, does your file actually make sense as a three-dimensional object in space? Is it closed? Is it manifold, meaning are there any leaks in the surfaces? How big is it? These are deceptively easy to get wrong if you're not paying attention. To understand what I mean, think about the question, how thick is a plane? If you were just to tell the 3D printer to print this plane, how many layers tall would it be? The answer, of course, is it's a trick question that has no thickness. The printer wouldn't even attempt it. It would just ignore this surface entirely and print nothing. If you actually wanted to print a flat sheet of plastic, you still need to extrude this shape and give it some height. Now let's look at this cube. Assume that this cube is perfectly 3D modeled. When you print it, how thick are the walls of this cube? How dense is the cube? Again, trick question. That's actually up to you and has nothing at all to do with the STL file. When you bring this STL into the slicer program, you get to choose how thick the walls are and how dense the infill of the print is. Regardless though, as far as the slicer is concerned, this cube makes sense because it's a solid and it's closed. And we know it's solid and closed because the faces are all joined together at the edges. There are no gaps. Every STL file created for 3D printing should be solid. But let's say that I were to delete one of these faces in Rhino. Well, now we've got a problem because this isn't a cube. It's not actually even a box with an open lid. That would look like this. No, this is just 5 infinitely thin planes just sort of arranged in a box-like pattern, but none of these sides have a thickness. So again, the 3D printer is just going to ignore this. Or it may try to print it and get it way wrong. Mistakes like this seem easy to avoid, but this is just an exaggerated example. You're way more likely to do something like this, like a cube with one side that doesn't extend all the way. Or this, a cube that's just 6 planes arranged together but not joined. Or this, an entire building made of cubes that never close. Any hole in the skin of your object will immediately render it non-manifold, and even if the slicer tries to make a reasonable guess as to how to fill that stuff in, you're probably going to have errors in the print. In your design, you've also got to worry about normals. Every surface on an object has a normal. Normals are a piece of information. They're vectors that define the direction of a surface. Think of them as little invisible arrows that mark a surface to define which side is the interior and which is the exterior. Normally, Rhino is smart enough not to mess this up. When you join surfaces to form a solid, Rhino can usually figure out how to make the surfaces all face the right directions. But if your modeling process is too reckless, or if you're twisting objects into impossible shapes, you may run into this issue and not catch it until you've got a whole bunch of flipped surfaces that can be a pain to reverse. I actually see normal issues happen way more often with SketchUp than Rhino. Let me show you one example of how they can happen.
One of these things is not like the others. One of these things doesn't belong. Can you tell which thing is not like the other by the time I finish this song?
See this shaded surface that's darker than the others? This shaded side lets you know that SketchUp thinks this is the interior side of the object's skin. To fix this, you can select the problem face, right-click it, and flip it. But if you're ignoring these bad normals until the end of your design process, you may find it difficult to track them all down and repair it once. There are many different ways to generate an STL file that the slicer won't be able to make sense of. We certainly don't have time to cover them all in this video, but as a general piece of advice, when you are modeling,
A, B, C. A always B, B, C closing. Always be closing. Always be closing.
always be closing. Every time you create a component, come in with a plan to close it. If you create a surface, know exactly what other surfaces you're going to connect to. If you're extruding a curve, cap it or use the solid option. When you're done with a component, check it against the properties window and make sure it says solid closed poly surface or closed extrusion. Don't just group things when you should be joining them. If something isn't joining that you think should, stop right then and figure out why it didn't. If Rhino tells you that your shape is open and you're not keeping it open on purpose, don't just move on. Get to the bottom of it then. Reconstruct the object if you have to, or keep building on it until it's closed and solid. You can use the Edge Finder tool to locate naked edges. Those are edges that are not joined to a surface, usually a good sign that your object has a leak in the surface. You should also avoid exporting multiple overlapping solids or grouped shapes. Instead, you should be combining solids into a single shape. That means you won't be able to target and edit those overlapping objects as separate entities. So there may be times when you don't want to Boolean union them together immediately, but come time to print, as a best practice, all of your shapes should be merged using Boolean unions into a single solitary solid before you export it. And you should be using Rhino's export selected with your object selected to generate your STL, not just export, because that's going to export the whole plate. That way, you make sure that you're only exporting the specific object you want to print. A lot of times when you're designing, you'll leave a bunch of scrap components, loose curves, and maybe some items that you copy-pasted but you didn't delete. You don't want any of this actually making it into the STL file that you send to the printer. So make sure that you select only the object you want to export, hit File, Export Selected. From there, choose the STL option under the File Extension menu, and you've got your STL. It's also worth mentioning now that if you intend to 3D print, you should always be modeling in millimeters. Because no matter what units you model in, when you bring it into the slicer program assumes that you mean millimeters. An STL file comes embedded with information about how big the object is, but the slicer only sees the numbers, not the units. So if you design an object to be 2 inches tall, the printer looks at it and says, oh sure, 2 millimeters tall, I can print that in 5 minutes. If you design a building that's 300 feet tall, it reads 300 millimeters. There are no simple buttons that let you say, oh, this is a 300-foot tall building, but let's print it at a 1/8 scale. 3D printers do not understand architectural scale, and they want everything in millimeters. So if you print an object, you should be figuring out exactly how big the physical, real-life product that you want to create is, and express that in millimeters. That means you'll have to do some math, and you'll likely need to change the units in your Rhino workspace before you export the file. The units set at the time of export are what matters, not throughout your whole design. Don't forget that you can use the box edit command to measure and adjust the scale of your entire model. Now at long last, you've got your file exported and you're ready to start 3D printing. So let's get oriented with Cura, which is the slicing software that you'll need to use to translate your STL into G-code. Remember, you don't need to have Cura installed to follow along with the video because we have a Cura station here in the lab for you to use, and to be honest, slicers aren't really that complicated. All they really let you do is bring in an object, preview it on a plate, scale it to different sizes, rotate it to different angles, and adjust a few settings. We're not going to go very deep into covering what all of these little settings do because realistically you shouldn't need to adjust them very much at all. If we're having to tweak with a lot of settings, it's because there's something wrong with the printer. You'll be switching between high speed and high detail settings, and you'll be adjusting things like the density of the object or whether to print the object directly on the plate or on a bed of plastic called a raft. But you're really not going to get much out of messing around with the fan speed or the nozzle retraction distance. Cura is an open source software that functions with hundreds of different 3D printers, so for more DIY machines, having all these settings here to tweak and optimize can be useful. But for Lulzbot machines, the default profiles should be all you really need. If you've downloaded Cura for Lulzbot on your machine, you'll want to make sure your setting profiles match the printers in the lab. To bring in the printing profile, when you first launch Cura, go to the drop-down menu on the top right of the screen and select Add Printer. You'll want to add the Lulzbot Mini 2 with the SE 0.5mm Aero V2 toolhead. Hit Finish to add the printer, and if it doesn't automatically switch to it, select the one that you want to use from the drop-down menu on the top right. We also have 2 larger Lulzbot TAS6 Aero Struder printers, and you can add those too. Just remember that when you create a G-code file for one printer, that file will not work on any other type of printer, so make sure those match. For the category setting, you can select all, then for the material setting, find the setting for verbatim PLA. From there, you'll select between high speed, high detail, or standard. These 3 choices are pre-made profiles for all the little settings contained down here in the custom settings area, which again, we're not going to mess with. So if you see all of these categories here, you can just go ahead and click the recommended button to get back to the shallow end. We're really only concerned with the thickness of the infill, whether the printer prints support material, and whether you intend to print a skirt, brim, or raft. More on these settings in a bit. But first, let's get an STL file loaded in here to work on. You can either drag and drop the file into the workspace, or you can hit the folder icon on the top left to open a file browser. Once the file is in, Cura may stall for a bit while it calculates how long the print is likely to take. You can see the progress bar near the bottom right, and it's going to do this every time you add, remove, move, rotate, or scale the object, so be prepared for a little lag time between each adjustment. To move your camera around the Cura workspace, place the pointer in the window and hold down the right-click button on your mouse. As you move your mouse around, the camera will orbit the printing plate. You can roll the mouse wheel up and down to zoom in and out, and you can hold down the middle mouse wheel button to pan the camera up, down, left, and right. If you click the object that you imported in, you'll bring up the Transform tool, allowing you to move it along one of the three axes. You can drag it around with the mouse or input specific movement distances in the pop-up window to the left. With the object selected, you can click the Scale button on the left sidebar. That's the third button down, below the File folder and the Move button. This Scale button, like Box Edit in Rhino, lets you measure and resize the extent of your object's bounding box. You can scale to a specific size in millimeters, or you can scale by ratio, inputting a percentage into these boxes. If you want to restore the object's original size, you can reset the scale. But never hit scale to max. I don't even know why that's an option. And make sure you keep uniform scaling checked, unless you're trying to warp your object on purpose for some reason. Below the Scale object is the Rotate button. This is the button that you'll use to turn the object along one of the three axes. This can be useful for testing how different orientations will affect the distribution of the support material. Again, you have your Reset button to restore the original orientation the object came in with. And there's another neat feature, which is the Lay Flat button. With the Lay Flat button, you don't have to get your rotation 100% perfect. You can rotate it so that it's pretty close to flat, and then hit the button to have Cura try to figure out the exact degree of rotation for you in order to get the object standing straight. One really useful feature in Cura is the Layer View. The Layer View will show you what the object looks like after it's been sliced. You'll get a full preview of how it's going to print the infill, any adhesion tools like skirts, brims, and rafts, where it's going to print support material, and sometimes it'll show you in advance if a bad model is going to cause errors. You can use the slider bar on the right side of the viewport to hide, reveal, and isolate layers of the print to get a closer look. On the right-hand settings panel, you've also got the ability to change the infill, which is the density of the interior portions of the object. Increasing the infill adds to the print's sturdiness at the cost of increasing the duration of the print. Most of your models won't really be under any great mechanical stress, so in most cases an infill of 10 or 20% can get you by. You can also enable gradual infill, which increases the infill density as the object prints upwards. This may help you get a smoother ceiling on an object if you have a wide flat surface at the top, but for the most part, I don't bother much with this setting. The next setting is called Generate Supports, which is one that I always click. Printing something that needs support material and forgetting to click this setting will likely result in print failure. And if your object doesn't need support material, Cura is just going to leave it alone. The only time I leave this setting off is if I'm trying to test something very specific, and in those cases, I'm going to stick around to monitor the print much closer, knowing that there's a higher likelihood of things going off the rails. Finally, you've got your build plate adhesion options, which include raft, brim, skirt, and none. What these do is help your object stick to the plate in different ways. Think about printing an object like a horse. A horse is like a big sausage of a torso and a head that will likely require support material, but the only parts of the horse that would touch the build plate are the little hooves. It's a shape with a small footprint, but a big shadow, and so while it's unlikely to warp, it's possible that the little hoof isn't going to be enough to keep that whole shape stuck in place. So a raft is a thick sheet of plastic that prints underneath the shadow of your object to ensure that the first layer gets good adhesion and provides a stable base of plastic for the support material to build up from. A brim, which is another adhesion option, is a single layer that doesn't print underneath your object, but just around the foot of the object on the first layer. It does a similar thing, but it takes much less time to print than a raft. And lastly, there's the skirt, which doesn't really do much to support your object in any way, but I still use it all the time, because it serves as a way to make sure the nozzle is purged of any old stray plastic before the print starts, and that the extruder gets a good flow going before the print starts building up. You're almost ready to hit start on your print, but first let's make sure the machine is ready. Turn on the power using the big red switch on the front. Then, use the display panel on the front of the machine to start turning the temperature up to 205 Fahrenheit. To do this, push the dial to bring up the first layer of options. Select Temperature, then Nozzle, and then turn the dial clockwise until you see 205. We're doing this for two reasons. Remember when I said it's important to keep the nozzle clean in order for the printer to calibrate correctly? Well, you can't clean cold plastic off the nozzle. It'll only come off in its liquid form, so we need to get that nozzle nice and hot so that we can use one of these handy green scrubbing pads to clean away the gunk. And we're going to do this extremely carefully because it's very hot, so don't squeeze the pad, just give it a couple of quick wipes. And don't use any other instrument to try to clean the nozzle either. If you don't see a scrubbing pad nearby, ask one of the helpers in the space to help you find one. The other reason we've got the nozzle hot is that plastic can't flow in or out of the machine unless the tip of the plastic strand is melted. If it's cool and solid, it's not going to budge. If there's plastic already inside the machine and you're good with the color inside, you can skip this step and just print. But if you want to change the spool, you'll need to unload the plastic inside. And you'll be doing this with the commands in that front panel, so don't just yank the plastic out. You can access the commands you need by navigating back to the Home menu. Then click Movement. Sometimes in the Movement menu you may see the option to move the X, Y, or Z axes, but you're not looking for those. You're looking to move the extruder, so click Extruder. Then it asks you for an increment, and I recommend using 1 mm increments so that you're not going too fast or too slow. If you turn the knob here in the positive direction, plastic will be fed downwards through the nozzle and melted out. And that's called extrusion. If you turn the knob in the negative direction, the plastic comes upwards and out towards the spool of the machine. That's called retraction. But here's another important reminder. Don't just rush to retract the plastic out of the machine right from when you've turned it on. See, if the plastic has been sitting inside the nozzle for a while, it starts accumulating this little glob of plastic towards the bottom of the strand, which can break off as you pull it out, leaving a chunk of plastic stuck inside the machine and above the nozzle. It'll get stuck in the channel that guides the filament down to the nozzle, but not at the hot end of the nozzle itself. Now here's why that matters. Now you've got a cold piece of plastic somewhere in that pipe, and it's blocking filament from coming in. No amount of heating is going to melt that clog. So if it gets stuck, we have to either ram it down or take the whole extruder apart and fish it out, and you'd be surprised how often it happens. Point is, when you go to retract the plastic up and out of the nozzle, make sure that you extrude some plastic down and through the nozzle first, and that'll help us avoid clogs. You should always be unloading plastic that's had at least 10 millimeters or so melted through the nozzle first. Once the extruder is clear, you'll want to use your fingers to push against the tension spring on the top of the extruder so that you can slip the filament through the hole and down the channel. If you're holding the tension spring correctly, you should not encounter any resistance until you hit the end of the nozzle where the plastic starts melting through thanks to the pressure from your hand. Then I let go and let the machine keep driving the rest of the filament downwards. But hold on, because there's another thing you gotta watch out for. This filament spool, you must always make sure that there's no tangles or kinks in the line. The filament should move off the reel smoothly and shouldn't catch or make weird clicking noises, because if there's a tangle in the spool, the plastic may stop flowing partway through the print. And the worst part is, the 3D printer has no idea it's happening. It'll just keep moving back and forth, thinking it's printing, without actually extruding the filament, almost as if the nozzle were clogged, but the problem is on the spool. Oh, and this same issue will also happen if you don't have enough filament on the spool to complete your print. You should not try to finish off the last of one spool during the print and expect to be able to reload it with a fresh one partway through. So always check your spool before you load it, and when you unload the spool, make sure not to just let the filament dangle freely. Take the end of the filament and run it through one of the holes on the rim of the spool in order to hold it in place for the next person. Then store the filament in one of the big gallon Ziploc bags so that it doesn't degrade with moisture. Now you know enough to set up your first print and send the G-code file to the TAS. There's two ways you can go about this next step. One is to connect your laptop to the printer directly using a USB cable. If your printer model matches the printer you selected in the top right drop-down menu on Cura, you'll have the option to just hit Print from USB and the job will start. The other option, if you have an SD card reader on your computer, is to save your G-code file onto the SD card and load the card into the printer in the little slot to the left of the display panel. From there, you can find the Print from SD card option onto the control panel and choose your G-code file. Either one of these methods will get your print started, and from there it's just a matter of waiting, monitoring for errors, and restarting your print if it messes up. When your print is finished, you can remove it using the flat end of a putty knife, making sure not to put downwards pressure on the blade, which may scratch it. Instead, use lateral pressure to wedge underneath the object and pry it up. When you're all done, don't forget to clean up your area, unload the plastic in the machine, store the filament, and let us know so that we can make sure the printer's ready for the next person. That wraps up our 3D printer certification video. You're now ready to take the assessment, which you can find by clicking the link on the DMC webpage. Once you've passed your quiz, you're ready to come into the DMC and start printing. We're always happy to help and answer any questions you may have. Good luck, and we'll see you in the makerspace soon.